This right here is a vintage Pioneer SX-1010 stereo receiver. The SX-1010 was Pioneer's top-of-the-line stereo receiver for 1974 and is capable of outputting 100 watts per channel into 8 ohms. So it's a very powerful and large receiver, weighing it at around 50 pounds. And as you can see, of course, it makes my relatively large Keysight multimeter here look quite small in comparison. Of course, right now I've got the unit set up for repair work, and so I've removed the faceplate and the top cover and other parts, but those did come with the unit and they're in very good condition. The faceplate is really quite flawless on this unit, and the dial glass is in great condition as well. The top cover is also very good, although it does have a little crack in the wood near the back that could be easily fixed. But I did get this unit for quite a bit cheaper than these normally go for, especially in such good cosmetic condition, because it is electrically broken. So this video is basically going to cover me attempting to repair and diagnose this SX-1010, and we'll see if we can bring it back to life. Now, before I go any further, I want to make a quick note that I'll be doing all this work with the SX-1010 plugged into a dim bulb tester. And there are many videos explaining what a dim bulb tester is and how to make one, so I'm not going to rehash that here. But I will say that the gist of it is a dim bulb tester limits the current available to the device that is plugged into it, the device under test, based on the wattage of a light bulb that is put in series with the device under test. So in this case, I'm going to be using this 72 watt incandescent light bulb here to limit the current available to the SX-1010 for the purposes of this testing. And this helps also bring down the voltage and, prevent any further damage, especially with a power supply issue or a suspected power supply issue. Running the unit with full line voltage for extended periods of time could just potentially worsen any issues that you may have. So it's good practice to at least start on a dim bulb tester until you've verified that everything is basically working correctly. Now we are going to start our diagnostics of this SX-1010 with the power supply section of the receiver. There are a few reasons in this case for starting with the power supply. First of all, the previous owner, who I gathered had some technical ability, informed me that he believed the power supply was the culprit. But that's really not the main reason. The main reason is that the power supply is generally a good place to start. Everything else in the receiver relies on the power supply to get the correct voltages that it needs to operate. So if there's an issue with the power supply, a major issue with the power supply, there's really no point in attempting to diagnose anything else with the receiver. You really need to start with the power supply, and once the power supply voltages are all sorted out and make sense, then you can get to the other sections. Of course, sometimes the power supply could appear to be having an issue that is actually caused by another section of the receiver. For instance, maybe there's a short in something and that's loading down the power supply so that the voltages look abnormal. That's something we'll consider, but in general, it's best to start with the power supply and, verify that the voltages you're seeing are at least somewhat resemble what you'd expect in a properly functioning power supply before you go on to doing anything else. So that's what I'm going to start with, the power supply section of this amplifier, the receiver rather. Now, if we look at the schematic in the service manual for this receiver, we'll see that there are two power supplies for this SX-1010. There is an unregulated supply, which provides the high current power needed for the power amplifier. And there is a regulated supply that provides positive and negative 56 volt regulated rails for other circuitry in the receiver. And from these positive and negative 56 volt rails, a number of lower voltage rails are derived. So also, if you look at the protection circuit, you will see that the protection circuit takes power from a number of these regulated power supply rails. So potentially an issue in the power supply could prevent the proper functioning of the protection circuit which is essentially what the previous owner of the amplifier suspected was occurring. So we are going to check out the power supply of this amplifier, specifically the regulated power supply, because there's much more that can go wrong in a regulated power supply than an unregulated power supply. So we're going to check out the regulated power supply, and also because the regulated power supply is what feeds the protection circuit, which is where the issue with this amplifier is, according to the previous owner. So yes. Before we get into checking voltages on this regulated supply, I want to take a look at the supply itself. Now, the regulated supply board is this board right here. And the unregulated supply board, well, actually, this board right here has the diodes for the bridge rectifier of the unregulated supply, which are these, in an odd package with this kind of metal thing running on top, and then two diodes underneath each of these. But anyways, these are the diodes for the bridge rectifier of the unregulated supply, and this is the regulated supply board. Of course, we have our filters for the regulated supply, and then we also have the other circuitry up here, and we have these relatively large heat transistors mounted to this heatsink right here, as well as a number of smaller transistors in here, and then we have the resistors and capacitors. You can see when you look at this board that some of these capacitors have been replaced. And you know, the telltale signs of that are, well, first of all, these are all old ELNA caps right here that look like they're from the appropriate, period. And if you look in enough receivers, you kind of know what these look like, but these old ELNA caps with the old ELNA logo are clearly original to the unit, unless someone replaced old ELNA caps with other old ELNA caps, which seems unlikely. But these, all these capacitors up here do not appear to be original. These, first of all, have extremely long leads that someone just seems like they were a little bit lazy when replacing these and didn't really push them in all the way. Of course, here you have an axial cap installed in what was clearly originally a radial cap position, so this is definitely not original. And also the plastic on these is a different color than what's typically in units of this era, and well, one of these is a Yageo cap. And yeah, anyways, there are many signs that these caps are not original to the unit. So it looks like this was probably a repair attempt replacing these capacitors. Another interesting thing worth noting that's perhaps more concerning is that some of these resistors appear to be in very bad condition. You can see these resistors are losing the paint that goes on the outside of them. It's actually like cracking and flaking off. I just removed some from that resistor right there. Obviously, that is not good. What it suggests is that these resistors have been exposed to a lot of heat, and that's probably what has caused the paint to flake off of them. And you can tell also that this area has gotten quite hot from the color of the PCB. If you compare this PCB, the color right here, to this one over here, you can clearly see that this PCB has darkened quite a bit. And you might think, oh, well, this is so much darker, it's just a different color PCB. But actually, if you look at the bottom, you can see they are basically the same color in the area that has not been exposed to as much heat. So that is not necessarily a problem. Sometimes these PCBs can darken quite a bit just from normal heat. I have a Pioneer M22 amplifier where the PCB is very, very dark, almost black, but everything, all the diodes on it that made the PCB so dark were working perfectly fine. They just got very hot. So it's not necessarily indicative of a problem if the PCB is darkened like this, but it does suggest that this area has become very hot, and that, of course, puts extra strain on the capacitors and all the other parts. And it could indicate also that these resistors have been subjected to an excessive amount of heat themselves, and so that's what's causing the paint to flake off. But anyways, all that is basically just to say that this board, there are indications of problems, and also there has been work done on it that indicates maybe someone in the past thought this was a problematic area. Of course, they only replaced these caps and they didn't replace the larger caps near the bottom of the board. Whether that was done for a particular reason or just because these caps are like more expensive and probably less likely to be in like a common cap parts bin. Impossible to say what the rationale is behind that. Based on the fact that these were all replaced, I have a feeling somebody was just shotgunning caps in here because these are probably from both voltage rails and whatnot. But we'll get to checking the voltages out and seeing what we can find on this board. So I think the first thing to check here logically would be the positive and negative 56 volt rails, since they are kind of the main rails in a way, and all the other voltages are just derived from those rails. So what I'm going to do is just check those, and when you check the service manual, you can see that the pins are marked. So one pin is marked 14, and that is the 56 volt rail, and another pin is marked 10, and that is the negative 56 volt rail. And the pins are labeled on the actual PCB itself. This right here is pin 10, and this right here is pin 14. So we can just turn the unit on. Of course, it is plugged into the dim bulb tester. And also I'm measuring just DC voltage to ground here. So I have one lead hooked up with a mini grabber to the ground side of one of the filter capacitors on the unregulated power supply. And I'll just be probing these directly with this. Normally I actually prefer to use mini grabbers or alligator clips for my voltage probing, but removing those in a video is not really ideal, so I'm going to use this normal probe here. Of course, I am using an insulator, helps prevent shorting the pins against each other, which will definitely create a new problem if you didn't already have one. So anyways, with this on the Variac, let's just turn it on. And the light does go on. This is a very large receiver, so I'm not too surprised, but it's nothing too excessive, so I'm not too concerned. And our voltage here is going to be a bit under 100 volts. So we're also operating at a reduced voltage in addition to being limited in current. But anyways, without further ado, let's first probe 14, which is the positive 56 volt rail, and see what we get. So we get 52 volts. That's pretty close, especially considering our line voltage is reduced by the dim bulb tester. That is pretty close to 56, so I don't see any immediate issue there. And now we can try the negative rail, which is pin 10. Try to do this without obscuring the camera. Okay, pin 10 is negative 28 volts DC. That is definitely not good, especially considering we just saw that the positive rail, which is a very, very similar circuit to the negative rail, except positive instead of negative, but the positive rail is at 52. The negative rail should be at something close to negative 52, and yet it's at negative 28. So I'm going to turn this off and say that already this is indicative of a serious issue on the negative rail of this regulated power supply, and certainly this is something that could cause our problem with the protection circuit. So now let's go back to the schematic, and maybe we can think about how to further investigate this issue. So thus far we've determined that the output of our negative regulated supply rail is significantly lower than our positive rail. And by lower, I mean an absolute value. It should be, assuming that the positive rail is functioning correctly, and I do think it is, that positive rail is outputting 52 volts. Given that the negative supply rail, as you can see here on the schematic, is basically a mirror image of the positive rail, I would expect that the negative rail would also output about negative 52 volts if it was functioning correctly. However, it's only outputting negative 27 or so, so I'm going to assume that the negative rail is malfunctioning. The reason that I assume the negative is malfunctioning and not the positive is because 52 volts is a much more rational and, logical output voltage than negative 27, because we are feeding the receiver about 95 volts. So I wouldn't expect it to be the full voltage necessarily, but I would expect it to be, you know, a greater than half for sure of the voltage that you'd expect on the rail with the full line voltage input. And 52 makes sense. But negative 27 is far too low. So as I see it, there are kind of two possible, you know, straightforward explanations that I can think of off the top of my head for why this would occur. And so I'm not going to claim to be an electrical engineer or anything, but I do have a kind of basic understanding of how the regulated supply works. And so at the top here, transistors Q1, which is a 2SD313P, and Q4, which is a 2SB507P, these are our control element transistors. These pass the actual current that goes through these regulated supply rails. And so if for whatever reason the control element transistor on the negative rail was dissipating way too much power, then that would explain why our voltage is low here. So one thing we can do is just take the collector voltage from this transistor and compare it to the collector voltage on the properly functioning power transistor up here, and see if the voltage drop on the negative rail is way higher than for the control element on the positive rail. And that would just indicate that our control element transistor on the negative rail is just dissipating way more power than on the positive rail, which would explain the low voltage. And then we could go into troubleshooting the other circuitry in the error amplifier, which is the two smaller transistors and all these other parts down here that provide the feedback for the control element. And we could, you know, attempt to troubleshoot that to figure out why, or maybe the control element itself has a fault. Who knows? But that would narrow down our fault to this specific board and this specific rail. Another possible explanation that would make sense to me was that maybe these negative supply is being loaded down by some sort of a short in one of the loads that is too high of a resistance to actually completely blow this supply rail or blow a fuse or something, but is still shorted enough to really pull it down. And to me, this voltage seems almost too low for that sort of a thing to be happening, but it's certainly, I think, within the realm of possibility. I could see that happening. So I guess the other option to test whether the load is drawing down the supply would be that we conveniently have resistors on the outputs of each of these supply rails, the negative 56 and the negative 24 volt rail, as well as the negative 13. Now the negative 13 volt rail has an 18k ohm resistor here. To me, 18k ohms is too many for it to be possible for this negative 13 volt supply to be dragging down the entire thing here. This resistor just seems like too high of a value. I can't imagine enough current being pulled through the 18k resistor to drag down the whole supply. So I'm going to assume that this isn't the problem, and I'm going to focus on R12 and R14, which are the 10 and 1.5k ohm resistors. And of course, we expect R14 to be dropping a significant amount of voltage because it is, you know, a relatively large value resistor, and maybe there's a good amount of current being pulled through here, and it's kind of a dropping resistor and whatever. But we can compare the voltage drops across these resistors to the positive supply ones, and if there's a big discrepancy, well, then that would tell us that we have an excessive current draw through one of our negative rails. So yeah, without further ado, let's get into testing both those theories, the control element power dissipation and the load current through those resistors. All right, now I've placed a mini grabber lead on our collector there of the negative rail. So let's check what this voltage is. Okay, so it is negative 44 volts. So the voltage drop across the negative rail control element is more than 10 volts. It's about 15 volts or even 16 volts. Whereas the positive rail only drops 2 volts. So clearly there is a big imbalance in that, and that's so that would indicate there's some sort of an issue, I think, with the actual regulation itself. And we could test the current through the resistors, but honestly, at this point, I feel like that is probably not even necessary because I think this is pretty incriminating for the actual regulated supply. But one thing that occurs to me now is that maybe it would be a good idea to check for AC as well. All these have been DC voltage tests, but maybe if we look for AC on the output of our regulated supply, maybe the presence of AC in the negative rail could explain why this transistor is working so hard and why the negative rail is working so hard to achieve its regulation. It seems to me that a lot of AC in the negative rail could maybe account for why this is exhibiting such weird behavior. And it's at least a worthwhile test to do. So I think I'm going to switch our DMM to AC volts here and turn this back on and see if there's, so this is still attached to the collector of our Q4 control element. So we're going to be seeing how much AC voltage is being fed into the regulated part of the supply from the bridge rectifier and filter caps, which are kind of the unregulated portion of this board. So I don't necessarily even know what a normal value would be. We'll compare it to the other one, but I wouldn't expect more than maybe a few volts or, yeah, a few hundred millivolts or something, but let's try this out. Okay, so we can see that there is about 15 volts AC going into our regulated supply. Obviously, I'm going to turn this off. 15 volts AC is not an acceptable input into the regulated supply. The regulated supply does reduce ripple, but 15 volts of ripple is not what it's meant to tackle. So the explanation for very high ripple being fed into our regulated supply would be just a dead filter capacitor. If your filter capacitor completely dies, then you'll basically be getting the full AC ripple of just the bridge fed right into the regulated part of the supply. And so what I would guess is that if we look back at our schematic here, is that the filter cap for the negative supply, which is C8 here, this 470 microfarad 80 volt filter cap, is probably dying, and what the fault it's probably exhibiting is a high ESR, and ESR is equivalent series resistance. So that basically means imagine a resistor in series with a capacitor, and that's what ESR is. A higher ESR means a higher resistance in series with the capacitor, and as you'd imagine, once the ESR gets extremely high, it's like partially removing that capacitor from the circuit, and with a very high ESR, you just get less effective filtering of ripple. So if that capacitor has a very high ESR, then our ripple isn't being filtered, and so we would get 13 volts of AC being fed into our regulated supply. And the regulated supply, I imagine, I'm not an expert with regulated supply design or anything, but I would imagine that having such a high AC voltage forces the regulated supply to work really hard and to drop a lot of voltage in that control element. And so that's why we're seeing such a low voltage on our output, because we have 44 volts on the input to this. So that is much closer to the correct voltage than we were getting before. And so now what I want to do is, just for reference, to remove this lead from here and replace it on the collector of the positive supply control element, so we can compare what the ripple should be coming out of the bridge rectifier and the filters. So you can see here we have 1.4 volts. Actually, it's decreasing quite a bit. Now it's settled down to about 170 millivolts. So obviously 170 millivolts is much, much, much lower than 13 volts. This is more what I would expect. So I think that to me is a very, very, very clear indication that the filter capacitor is one of the culprits in the issues with the supply. Now, will replacing the filter capacitor necessarily fix the supply? That to me is less clear, since some of these resistors have already suffered damage and whatnot, and who knows what else has happened with the supply. Maybe even the capacitor died as a result of something else that happened, although that doesn't seem likely to me since it is a filter capacitor. But yeah, we're going to have to keep looking at the supply, and replacing the filter might not fix it, but it definitely seems like the next logical step to do. Yeah. So the new parts arrived, and what I've done is I've gone ahead and marked these two capacitors with C8 and C9. These are our two force 170 microfarad filter capacitors. So I'm now going to desolder both of these, and we can use an ESR tester, which I have right here, to test the ESR of both of these capacitors and see if we can validate my theory. All right, so now that we got our caps desoldered right here, C8 and C9, let's do the ESR test with this ESR meter right here. First starting with C8. And the leads are connected properly. They're making good contact here, and you can see the reading is still over limit. So this is a very, very bad capacitor. The ESR is extremely high. If we test C9, which was on the good power supply rail, we see that the ESR is going to be 0.17 ohms. So obviously, you know, that's a real ESR. That's actually a good value. This capacitor is perfectly fine. But obviously C8 here is not fine and, you know, is basically useless as a capacitor at this point. So that would certainly explain why our negative rail was not working properly. And now, when we replace these capacitors, I fully expect that the regulated supply will perform exactly as it's supposed to. And so we have our new capacitors here. I actually bought new caps for the whole board while I'm at it, especially since if one failed, you know, maybe this board was getting really hot. I just want to replace them all just in case. These are really high quality Nichicon automotive caps. They have a 125 degrees Celsius rating, and they have a very long lifespan, so these will last for quite a long time in this regulated supply. And I have caps for the whole board, so we're going to replace the caps for the whole board. I also purchased new semiconductors for the whole board, except for the bridge rectifier diodes. But I'm not sure yet whether or not I want to replace all the other semiconductors because I don't have any reason to suspect there's anything wrong with them. If I did replace them, it would be purely because I bought the parts. I bought the parts just in case I would need them, in case there was anything else wrong with the board. And the resistors, based on the resistance testing I've done so far, the resistors seem to be totally fine. The resistances are the same on the positive and negative rails, so nothing really seems to be out of whack there. So I didn't purchase new resistors. And, you know, yes, the coating is flaking off of some of those resistors, but I don't suspect that's a real issue. It's probably just cosmetic. But yeah, so let's replace, first we're going to replace these two caps right here, and then we're going to turn the supply back on with all the other original caps. All right, so our new capacitors are installed in the place of C8 and C9 right here. So I'm going to turn this on and see what voltage we have on pin 10, which is our negative supply lead. And it should be around negative 52. But yeah, I guess we're going to find out if that capacitor was all that we needed to fix to get this supply working. All right, and we can see our negative supply rail is coming up. It's getting close. It's 52.9, so I think it's still going up a little bit. I think it's going to even out at about 53 or something like that. But I think that's a good indicator that we did take care of the issue. And let's change this to AC voltage. And you can see that our AC voltage here is, what would that be, about 40 millivolts. So I think that was even better than we had on the positive supply with the old capacitors, although I'm not, my memory could be wrong, but in any case, obviously that's a far cry from the, 10 or whatever volts we had on there before. It's been a while since I shot the last part of the video that you watched, but certainly I would say that this regulated supply is working properly. All right, so as you can see, I've completed the recap of this regulated supply board. Obviously we got C8 right here, which was our culprit in our issue, but I also replaced all the other caps with these Nichicon UBT high temperature, long lifespan capacitors that'll last a while, even though there's a fair amount of heat in this area. In addition to replacing these caps, I also replaced the 3 transistors in the positive 56 volt rail and the 3 transistors in the negative 56 volt rail. I replaced the 2 smaller transistors right here that are part of the feedback and the voltage reference circuitry and whatever. So that's these 2, and then also these 2 over here that are difficult to see. And in addition, I replaced the big TO220, that's the control element in each rail of the supply. So yeah, when I replaced these ones, I discovered, first of all, that they had already been replaced actually once. The soldering was clearly not factory on these TO220s. So they had already been replaced, maybe as part of the attempt to fix this unit previously, along with the replacement of some of the capacitors. Whoever tried to fix this also replaced these. Of course, they weren't the problem, so it wouldn't have done anything. But when they put them back on, they did not use any thermal compound. So there was no thermal grease at all. There is a mica washer, but they had done no thermal grease, so there was very poor contact thermally between the transistor and the heatsink. Of course, these transistors are running well below their rated specs, so I don't think they get very hot in normal operation at all. But nonetheless, I decided to add some thermal compound when I replaced them, and I wanted to replace them to make sure they were properly utilizing the heatsink that's supplied right here. So anyways, yeah, I'll put the parts list for this whole refresh of this board. I'll put the parts list in the description of the video. There are a number of subs that people recommend for these transistors. I did choose to go with the tip 42, tip 41 and 42 parts, as opposed to using the MJE sub that a lot of people use. The reason for that being that the MJE is a higher speed transistor, and these are a slower transistor that's more similar in that respect to the originals that were in here, just to prevent any high frequency weirdness that might happen with this circuitry in here. So now I think the next thing to do is to give this a larger bulb on the dim bulb tester and see if we get our protection relay to pull in. And if the protection relay pulls in and the power amp section is working, I think that this specific repair is then complete. And whether or not there are other issues in the preamp section of this and whatnot, I have no way of knowing that, but with regards to the specific issue this came with, which was the protection circuit not pulling in, I think that we're probably close to having that resolved. So let's swap a bigger bulb on the DVT and see what happens. So unfortunately, I turned the receiver on off camera and it still isn't coming out of protection even with a larger 150 watt bulb. So I think it's time to move on to troubleshooting the protection board itself. And the first thing I want to do is check our power supply voltages, just to make sure our wires are making good contact. Of course, we already know the plus 35 and negative 13 volts are present on the regulated supply board, but we just want to make sure they're also present on this board as kind of a first thing to check. And there's also pin 12, which is supposed to be 7.5 volts AC. I want to check that that's present as well. So I'm just going to turn this on and do those checks real quick. So let me get the multimeter in frame here if possible. All right, so let's start with our 35 volts, which is pin 11. All right, that looks good. and our negative 13 volts, which is pin 2, negative 12. So it's a volt off of negative 13, but I think that's probably not our problem. And then AC 7.5 on pin 12. So switch to AC. Okay, it does not look like we have AC 7.5 on pin 12. It looks like we have, maybe there's an intermittent or something in here. Yes, he had jumped up to 4 right there. So yeah, so we're missing that voltage. I'm just gonna go look around the back, and I think what I might do is just run a jumper from the back of the board to the front, just to grab that voltage right off of our the fuse that it comes from the transformer, and then we'll just jumper that in and see if that changes anything here. All right, so now I've run a jumper just from the fuse holder that has the 7.5 volts AC on it. I've run a jumper to the front of the board. I think what's going on is that the little post or the pin that has the wire wraps on it that bring the 7.5 volts off of the fuse board, I think there's just a bad solder joint in that pin. So that pin isn't making contact anymore. So now I'm grabbing the voltage right from the fuse holder. And that also has caused our dial lights to go on over here. And it's caused our current draw to increase. So I think that that pin needs to be resoldered. And I'll do that later. But for now, I think just having this jumper right here, bringing that voltage will be sufficient. So just to show you that we do now have this voltage on the pin, I'm going to probe this. And you can see it's 5.6 or something. It's not focusing properly, but it's 5.6, so it's not quite 7.5, but our line voltage is still low. So I'm going to assume that's why. And I don't think that's a big enough difference to be the cause of our problem. So let's start checking voltages on the board itself now. There are some labeled voltages based on the schematic here. One of them is 20 volts. So I'm going to check 20 volts at the base of Q5, transistor Q5, and I'll explain why in a second. Okay, so at the base of Q5, we have 7.6 volts. And I'm going to pull up the schematic and show you why I chose this transistor to check in a second. But before we do that, let's also check the collector of Q1 and Q2. All right, let's turn this on. All right, that is also 7.2 volts, and the collector of Q1 and Q2 are actually tied together if you look at the schematic. So there's really no point in testing Q2 once we've already tested Q1. But yeah, so we've got 7.3 volts there as well, same as at the base of Q5. And one more thing I want to check, which is the collector of Q3. Let's turn this on. Okay. Ooh, so here we have 35 volts. All right. Okay, so with those measurements done, whoops, I think we're getting bad contact here. Yeah, the connection between the mini grabber and the multimeter lead, the banana here, is a little spotty, but anyways. And the last thing I want to do, just to be 100% sure when we go in and label all these voltages on the schematic, is to also check the collector of Q4. All right. Okay, so collector of Q4 is only 7.3 volts. All right. So with those voltages taken, I think I have a suspicion as to what's going on here. So let's go label these voltages on the schematic, and I think we might be able to figure out what our issue is. All right, so as I said earlier, I'm not going to claim to be an electrical engineer or anything, but I do think I understand this circuit well enough to explain basically what is going on here and to be able to troubleshoot it. So intuitively, the first thing we notice if we look at this circuit is that Q5 looks like a switch. Q5, first of all, Q5 runs right into Q6 and Q7, and Q7 is the transistor that drives the relay. So it's logical to assume that Q5 here is acting as some sort of a switch, especially since it ties to all the other circuitry, as we'll see in a second. And another thing is that Q5 is a PNP transistor, and the way it's configured in the schematic, which we would assume the schematic is showing the state where everything is correctly working, in other words, the state where the amplifier is out of protection. What we're going to assume here is that Q5 is acting as a switch, and this is, in the default state, a deactivated switch, because the base voltage on Q5 is higher than the emitter voltage. And with a PNP transistor, if the base voltage is higher than the emitter voltage, you're not going to have current flowing. The base is supposed to be negatively biased relative to the emitter if you want current to flow through your transistor. So this is a switch, and in the default state where everything's working right, the base voltage is higher than the emitter and it won't conduct. But as we just saw when we tested the base voltage of Q5, our base is in fact at a lower voltage, in other words, negative with respect to the emitter. We have 7.5 volts on the base, and I didn't show the testing of the emitter on camera, but trust me when I say it's about 18 volts, it's about right. So actually, what we need to do is determine why our base voltage is low. Now, if you look at the rest of this circuit, you can see that the base of Q5 is tied by diodes to the collectors of Q1, 2, 3, and 4. So let's take a look a little bit at how I think this circuit is operating. Q1 and Q2, their collectors are connected right to the base of Q5 by a diode. Q3 and Q4, their collectors are also connected by a diode to the base of Q5, but they connect to resistors that connect to the 35 volt rail as well. So R18, which supplies the voltage for Q5, the base, R18 is a relatively high value resistor, and what that tells us is that when the current draw across R18 increases, we're going to have a pretty big voltage drop across that resistor, that R18. So you can see intuitively that if a lot of current were to flow through Q1 and Q2, the current draw across D5, that diode that connects those to the base of Q5, that current would increase. And if there was a lot of current being drawn through D5, then the current draw across R18 would increase. And as that current increased, that voltage would get pulled low. And as that voltage gets pulled low, you can see that Q5, the switch would activate and we would go into protection. And of course, the collectors of Q3 and Q4 are also tied to the base of Q5, but they're tied by these diodes. So if the base of Q5 gets pulled low, it's not necessarily doing anything to the voltages on Q3 and Q4's collectors. So each of these circuits kind of operates somewhat in isolation. And of course, you can see that the collectors of Q3 and Q4 are tied by diodes to the base of Q5 as well, as we just said. So what that also means is that normally Q3 and Q4 draw their collector voltage and current through resistors R13 and R14, which are 15K resistors, so they're a lower value than R18. And as we just saw, the voltage on the collector of Q3 is like 34 volts. It's basically the same as the regulated supply rail voltage. So what that means is that normally, I think in the correctly operating state, the voltage at the collector of Q3 is higher than the voltage at the base of Q5, so there would be no current flowing across diodes D6 or D7 at all. But if like Q1 and Q2, if Q3 and Q4 were to start conducting, you'd get more voltage drop across R13 and R14. And as you go, the voltage at the collector of Q3 and Q4 might become lower than the voltage at the collector of Q5. And at that point, current would start to flow through D6 or D7. And just like current flowing through D5, the effect of that would be to pull the base of Q5 low, to pull that voltage low, because that voltage is being drawn through a 150K resistor. So that voltage would be pulled low if current flowed through Q3 or Q4. So basically, my assumption about how this protection circuit works is that normally the base voltage at Q5 is 20 volts. That means the switch is off and everything is good. However, if Q1, 2, 3, or 4 starts to conduct, then current is pulled through D6, D7, and D5, and that pulls the voltage at the collector of Q5 low. And so, as we saw when we tested the amplifier, our voltage at the collector of Q5 is being pulled low. It's only 7.5 volts. And so we can tell, based on the voltages that we collected, which of these parts of the circuit is at fault. Because as we said, on the collector of Q3, we had 35 volts. Obviously, that's a high voltage, so it's not the culprit in pulling our supply low. We also had 7.5 volts at the collector of Q1 and Q2. However, we can see that because Q1 and Q2 draw their collector voltage from the same exact source as Q5, they're going to be pulled low regardless of whether or not they're at fault here. The culprit here is actually Q4, because Q4 also had 7.5 volts on the collector, but the only reason that Q4 would have 7.5 volts on the collector is if Q4 is actually conducting current. Because as you can see, if Q4 were not conducting current and it had a normal current draw through through R14, it would be 35 volts. It would be happy just like Q3, and there would be no voltage difference and no current flowing through D6. But since this is low, what we can conclude is that Q4 is conducting. The current draw through R14 is high, and that is drawing current through D6, which is pulling Q5's base low, and in turn pulling the collectors of Q1 and Q2 low as well. All right, so now that we've identified Q4, or the circuitry around Q4, as our culprit, I want to just test the emitter and base of Q4 as well, just to make sure that those voltages aren't causing our problem. So first, this is the I think the emitter. Which one did I put? Yes, this is the emitter of Q4, and it's supposed to be negative 0.6 volts. So let's turn this on and see what we've got. Yep, it is about negative 0.67 volts. So that looks good. And really quickly, I'm going to switch this to the base, and we'll do that as well. The base is supposed to be 0 volts, and this is the one that actually connects to our inputs. So it's sensing whether or not we're supposed to be in protection. So let's do this. It's supposed to be 0, remember? And it's pretty damn close to 0, 0.03, 0.02. This is actually should be the DC offset that we're getting. And combined, of course, from both sides of the amplifier and put through resistors, but it looks like about 0.02, negative 0.02. So I would say that is perfectly fine. I don't think that this small amount of voltage here accounts for us being in protection. I don't have any way of knowing that for sure, but I mean, I could like properly model and sketch out how the circuit is working and stuff, but just intuitively, I don't think that 0.02 volts on the base is far enough from 0 volts to explain why we're in protection. So I'm going to turn this off again. And I think what we're going to do is try desoldering Q4 diode testing it, maybe replacing it if I have the right substitute, and seeing if that clears up our protection issue. So let's get to that. All right, so really quickly, I just flipped this board over and I'm holding the camera now, but as you can see, it looks like someone already tried replacing these transistors, and the soldering here is atrociously bad. Look at, I think this is the base of Q5. It's not even connected. Can you see that moving around? I don't know if you can, but that is a terrible solder joint. Not even a solder joint. So what I think first thing I'm going to do is just resolder all these terrible joints and see if that fixes something, because some of the things on this board are not even making proper contacts, so let's do that first. All right, so I've gone through and resoldered the bad solder joints that were around Q3 and Q4. Especially Q3 had some really bad ones. The base was barely connected. And then I've also gone through and resoldered all the pins that connect to the wire wraps, because those are a known weak point on this receiver. But anyways, I've got my mini grabber lead here hooked up to the base of Q5. Let's do another test and just see if maybe all that was wrong was those solder joints, and maybe without replacing anything, we'll actually get this receiver to power up and go out of protection. So let's turn this on and look for our 20 volts that we're supposed to have here. And it looks like it is climbing, and I just heard the protection relay click. So whatever it is, it must have been one of those bad solder joints on the other side. Now I'm curious to check the voltage on the collector of Q3. Remember, we checked it earlier and I saw 34 volts. I assumed, oh, that's good because it's a high voltage. That means it's not pulling down the base of Q5. But now that I think about it, Q3 and Q4 are kind of tied together, and so maybe it was like an imbalanced current draw. If Q3 had the base was just floating or whatever, maybe there was some imbalance between those two transistors, Q3 and Q4, that was causing Q4 to conduct. And I don't fully understand how the circuit with Q3 and Q4 is functioning here. If I took the time to trace it out, I could probably get it, but I'm just curious to see if this voltage has come down on the collector of Q3. So let's try that out. And yeah, it looks like this has come down to about 17 volts, which makes more sense. So it looks like our issue was just some of those bad solder joints around Q3 and Q4. Who knows which bad solder joint it actually was. The base of Q3 is supposed to be 0 volts. So it seems to me like if it was floating, that wouldn't necessarily be an issue, although it is supposed to be tied to the same point that the collector of Q4 is tied to through capacitors C3 and C4, which it looks like are just blocking DC. But in any case, so maybe that's like some sort of an AC balancing thing. I don't really know. But yeah, in any case, it looks like the emitters of Q3 and Q4 are also tied together. So maybe it was a bad solder joint on the emitter of Q3 that was causing the issue. I don't really know. But anyways, it looks like our protection issue is resolved, so that'll be about it for this video. Perhaps I could have checked for bad solder joints as kind of the first thing that I did here, but you know, live and learn. I mean, it was nice to go through the schematic and kind of think about what was going on in the circuit, even though ultimately it wasn't necessary. I probably could have just flipped this board over, resoldered everything, and fixed it that way without really thinking about what was going on here. But anyways, just to close out this video, I'm gonna plug some speakers into the output here, plug my phone into the input, and see if we can get a little bit of music out of this receiver. I don't even necessarily expect it to sound good. I think that there is a noisy transistor in one of the channels. So I think there might be a few more videos on this specific receiver, but at least the main issue that this came to me with, being stuck in protection mode, has been addressed. And there were kind of two separate issues. Ultimately, there was the power supply issue and this issue. I suspect that whoever tried to repair this just honestly created more problems for themselves by the bad soldering job on this board, that probably made them, I think they were running around in circles when repairing this. They recapped a few things. There's new caps on this board. These two caps are new right here. I think they were shotgunning parts and kind of creating issues, which shows that, if you go through these things without having a real like step-by-step method, if you go through with the approach of just, oh, look at this board, it seems bad, I'm gonna replace some random stuff and see if it works, you're just gonna get frustrated and it's not really gonna be successful. If you wanna go through these receivers, shotgunning has its place, and certainly these issues might have been replaced by shotgunning. If you'd just gone through each of these boards and resoldered everything properly and replaced all the caps, these issues would have been fixed. But it is much faster and easier to go through methodically, and sometimes you get an issue that can't be fixed by just recapping. Maybe it's a bad resistor, maybe it's a broken trace. It's good to just, start with the power supply, go through each board, try to figure out basically what you expect and see what is different from your expectations and do it that way. But anyways, without further ado, let's put some speakers on this thing and see if it sounds halfway decent. All right, so to close out this video, let's just do a quick test here on the speakers. I'm actually just going to use this function generator playing a 1K sine wave at 5 millivolts, and I've got that plugged in with an RCA splitter right here into both our left-right inputs. I'm using the power in inputs to bypass the preamp section, just so we're testing just the power amp. The preamp could have its own issues, who knows. And yeah, I've got this DMM reading the DC offset from this channel right here. I forget which one it is, I think the left. But anyways, and I've got our speaker outputs, of course, plugged into these two little speakers right here. So yeah, let's just play our sine wave and see what we get. All right, so you can probably hear that sine wave. It's pretty quiet because I've only got 5 millivolts, but of course I can turn up the amplitude here and it gets louder and quieter. I can tell just from listening to this that the left channel is quite a bit louder than the right channel. Yes, which one's this? Yes, the left channel is quite a bit louder than the right channel. So yeah, we've got some sort of a channel imbalance issue here that's gonna need to be addressed. But yeah, so we'll have to get to that, and there's gonna be more videos on this receiver. I'm guessing I might do a recap video after I do the amplifier board repairs and signal tracing and whatnot. But anyways, I'm going to say that our protection issue is resolved successfully, and so that's going to be it for this video. Thanks for watching, and please, if you have any comments, leave them below. Any feedback is much appreciated.